Okay, so I'm going to continue to talk about chapter 3. Chapter 3 just talk about a simple concept, which is called a moment. But the moment is always due to a force. There's 3 types of moment we talk about. The first type of moment is called a moment of force about a given point. The second kind of moment is called a moment of a force about a given axis. And the third one is a moment due to a couple. And of course, we're going to talk about what I mean couple. There's 2 special forces following certain requirement. Okay, so last time I talked about this. Today I'm going to introduce the second type of moment of a force about a given axis. Okay, but no matter what, all moments are related with forces. Okay. Of course, the final goal in this chapter is to do something like this, because we don't want to see a lot of, in reality, of course, there's a lot of forces acting on the rigid body, but we want to simplify this scenario so that we're going to finally end up with just one equivalent force and one equivalent moment. This altogether is equivalent to this one, but it's much easier to deal with this kind of situation because you only have one force and one moment. So the maximum is 2 quantities. But at beginning case, this one like this, you have 3 forces where you have 100 forces. Of course, that's not very convenient, right? So this is our goal at the end of the chapter. So we'll show you after we introduce all these 3 kind of moment, we're going to finally reach to this stage. That's the end of this chapter 3. And then we're going to use this one in chapter 4, solving real engineering problems. Okay, the first kind of moment of a force about a point, by definition, that is R cross F. So that is a very important equation allowing us to calculate a moment of this force about the arbitrary point O, which is R cross F. R is a distance, but it's vector from the point you want to calculate the moment of to the point that force applied on. Okay, so that's the definition of R cross another vector, which is called the force. And how to calculate force vector? Well, this is what we learned in the previous chapter. Okay, so this is the fundamental definition of the moment. Almost all 3-dimensional problem we're going to talk about is to use this equation. Okay, use this is the only equation to calculate the moment of a force about a given point. For 2-dimensional problems, if we want to calculate a moment of a force about a given point for 2-dimensional problems, sometimes you can use this equation. Sometimes you can use the other equation as I called F times D. And that is this equation, or here. As long as you can identify counterclockwise as positive or clockwise, which you use a negative sign to indicate. But I'm not saying you use this method can solve all 2-dimensional problems. Sometimes you may see a challenge to calculate this D, which is called the shortest distance from the point you want to calculate the moment of to the force line. Okay, if this is a force line, you draw a straight line, which is shortest distance, that means 90 degrees, and as long as you can calculate the distance from this O to this one, shortest distance, then you can get a problem solved for 2-dimensional problem. But sometimes you have difficulty. So last time I showed you one example to calculate the moment of a force about the point, okay? And I was using what we call F times D, because for this problem, D is easier to calculate. If from this simple geometry you have a force going down, what is the shortest distance from the point you want to calculate the moment of to the force line? This is a force line, and that's D. That's very easy because you know the 60 degree, you know this is 24 inch, then 24 inch times cosine 60, you get D. Okay? So, but some other problem you may have difficulty to calculate D, then you may think about to use the original method, which is called R cross F. Okay? So I just want to spend a few more minutes to recalculate the moment of this force about this point using what we call the R cross F, even though it's a 2-dimensional problem, and you know you already solved this one. So let me just quickly show you, just in case you want to use R cross F, you can also have the job done. I think I can do. Okay. Is it focused? Okay, so instead of using F times D, so we say method 1 to calculate the moment magnitude is F times D, and you get this down as I showed you previously. Now I'm going to use another way to solve the same problem, which is called moment equal to R cross F, even though it is a two-dimensional problem. Okay, so then what we're going to do is to figure out this R and is to figure out this F. That's it. And then you do the cross product. So the first question is, what is R? What is R? R is a distance vector from the point you want to calculate the moment. That's point O. To the point the force applied on. That's this point. So then this R is basically from the point to the other point. And then cross F. So we want to calculate distance vector. If you want to use R cross F, you should first establish the Cartesian coordinate system, even in its two-dimensional setting. So for example, I call this is X direction, and this is the Y direction. Okay, you set it up. Or you can call this one as the original point. You can have X, Y. There's really nothing wrong. You can do whatever you like. Okay, but in order to use this method, you basically need to establish or set up the two-dimensional Cartesian coordinate system. After we get this, then we got a distance vector from O to A, which is A subtract O, right? So it's A subtract O. So that means you have the two components of A, this point. Now we have the original point here. What is the X component of this A? The X component of this A is 24 times cosine 60. So this is the X component. And Y component is 24 times sine 60 degree. Okay, so these are the two components at point A. That's the end point. Subtract. Subtract the start point. The start point, that's point O, which is original point. Well, that's a 0, 0. That's easy, right? And then cross F. We're going to figure out F separately. Okay. So this one, subtract 0, that's 24 cosine 60. And this one, subtract 0, is 24 sine 60. And then cross F. Now let's talk about force F. So this is the vector which is equal to the magnitude multiplied with the lambda, right? So what is the magnitude of this F? And what is the lambda, which is the unit vector in that force direction? So again, we have 24 cosine 60 and 24 sine 60 cross F. What is F? Well, by looking at this original red force acting on point A, so the magnitude equal to 100 pounds. Okay, so that's 100 pounds. You may say, wait, this 100 pounds going down. Is the magnitude equal to negative 100 pounds? No. The magnitude is always positive. So we're going to determine the direction, whether it's going down, going up, or going to the right, going to the left, or whatever. That's separate. That's a direction. So the magnitude is always positive because that's a physical quantity. Just like when you talk about volume. Okay, when you talk about area, it can never be negative. Okay, that's a magnitude. It's 100 pounds multiplied with lambda. Lambda is a unit vector in that force direction. So this is a force direction which is going down parallel to y direction, but it's going down. So then this is negative j. Okay? So in other words, if you want to write this kind of components, then you can write the x components of the force is 0, y components is negative 100. That's also fine. So sometimes I use A comma B to show a two-dimensional vector, or you can write AI plus BJ. Okay, so either way, sometimes I just write this, which shows a two-dimensional vector, or sometimes you write AI plus BJ. That's the same thing. Or three-dimensionally, if you say A, B, C, which are the three components of that vector, That is equivalent to AI plus BJ plus CK. So either way, sometimes I write this way, sometimes I write the other way. Okay. Now back to this. Back to this. We have this combined as 24 cosine 60. This time I use I plus 24 sine 60. I use J and cross 100 negative 100J. Okay. So now we need to do the math. Okay. So cross product. So first term cross with J. I cross J. What is I cross J? If you go back to look at my slides, I cross J equal to K. So then you have 24 cosine 60 times negative 100, and then I cross J. What is I cross J? That's K. And second term, J cross J. What is J cross J? So when we have a cross product between the same vectors, then it's 0. Okay, so then yeah, 0. Okay, so then you don't have to worry about the second term. So then what we finally end up with, move up. So cosine 60, you punch your calculator, that's half. Half times 24, 12. 12 times 100, that's a 1200, right? Negative 1200. And finally you need to write the unit, that's in terms of pounds, and the inch, and then K. So this, in fact, is the answer. If you want to switch back to what we call the clockwise, counterclockwise, that's also fine. If you want to say this moment is equal to 1200 pound inch, that's a magnitude, and then the negative sign means clockwise, that's also fine. So either you use this method 2 or you go back to look at method 1, the final answer should be the same. And here is the final answer, right? So either way, you may say, why? Here we have a K because we already established a two-dimensional coordinate system, then obviously I cross J equal to K. So whether you're going to write this K or not, or use this way, that doesn't matter. The two methods always finally give you the same answer. So the question is, which method you want to use for two-dimensional problem? Three-dimensional problem, most likely that's the only one method, that's R cross F. There's no choice, no options, right? Two-dimensional problems, sometimes you use F times D, sometimes you can use R cross F. If you encounter a problem to identify the shortest distance called D. Okay, so the bottom line is it's really up to you, but the answer should be the same. Any questions? Okay, so now let's move to another example I briefly talked about last time as well. This one. So this is a typical three-dimensional problem, calculating the moment of a force about a given point. So we see a rectangular plate here, supported by A and B here, and also in addition supported by a wire or say cable CD. So we know the magnitude of the cable CD is 200 pounds, 200 Newton. So now we need to determine the moment about point A of this force exerted by the wire at point C. So at point C, there is a force given by this cable. So then obviously because the cable can only sustain tension, so then that force has to go from C to D in this direction, not going down. So this is the force. Then what is the moment of this force about point A? And that is a question from this example, right? So this is a three-dimensional moment calculation problem. Obviously there's no options, so you just need to use this equation, right? So R cross F. So what you need to do is to identify R and identify F, and then you do the cross product, and that's the end. So whatever result you get is supposed to be the answer. Okay? So how to get R? So for this problem, how to get R? By definition, R is always from the point you want to calculate the moment of to the point that force applied on. So then obviously R is from A to C. From A to C, then you need to use C subtract A, right? So C subtract A. Then you need to get the three component of point C, you need to get the three component of point A, and then you use C subtract A. And then before doing that, you need to establish three-dimensional Cartesian coordinate system. If the question gave you the three-dimensional Cartesian coordinate system in general, then go ahead and use that. Just in case, if the question does not give you, then it's your responsibility to establish one. establishing a coordinate system is not difficult, right? But you need to make sure normally you have x, y, and z, and also x, y. After x, y is finalized in the z direction, you have to make sure it's follow the right-hand rule, not the left-hand rule. Okay? So if x is this, y is this, then z has to go this direction, not going to the opposite one. Okay? Because the right-hand rule. So we established original point O and the x, y, z's, and obviously you can find out the 3 point here. You can find out another 3 components here using c subtract a. That's you finally end up with this r vector. Okay. So once we got an r vector, then we need to deal with the second vector, which is called the force vector, f. What is a force vector in three-dimensional setting? Well, that's the stuff we learned in chapter 2. In chapter 2, we normally use a force vector, which is a kind of, on the left-hand side, split it into 2 parts. One is the physics part, that's called the magnitude, and one is the math part, which is called lambda. So F for this problem equal to 200 Newton given in the previous slides. Now we just need to determine the unit vector in that force direction, right? So this unit vector is different from the distance vector. Distance vector just from the end point subtract the start point. The unit direction vector is basically end point subtract the start point and then divided by the distance. So you have something additional. So again, picking up 2 points in this force direction, obviously you're going to pick point D and point C, right? So this force is from C to D, then you're going to use a D subtract C. D minus C, that's a distance vector, but don't forget, divided by, have this quantity divided by the distance, okay? So D subtract C, this is what you got, and divided by square root, this square plus this square and plus this square and square root, finally you get 0.5. So this is the final three-dimensional force vector, or in other words, this is the x component, this is the y component, and this is the z component. So once you are done with this one, now you just plug in this f back to here. You need to do the cross product between r and f. And then it's really up to you how you're going to do the calculation. Okay, you can do this term by term, so totally supposed to have 9 terms, but 3 of them are 0 because that's going to be I cross I or J cross J or K cross K. So you only have a 6 term left. And for some time there's maybe 0 term, then you can less term. Okay, or you can use this equation, which is a definition as well from R cross F. You always list this 3 by 3 matrix. The first row is ijk, second row are the 3 components from the r vector, and then the third row are the 3 components from the force vector, and then make sure you do the determinant of this 3 by 3 matrix. No matter what, you finally end up with a solution. In terms of solution, make sure you finally write those units. Okay, any questions? So I'm not going to talk about the details, but they are pretty much straightforward following this kind of procedures. Okay, so this is the first type of moment we introduce, which is called the moment of a force about a given point. Now I'm going to talk about the second kind of moment, which is the moment of a force about a given axis this time. Okay, so this is the picture, or this is also the picture we're going to frequently use when we talk about the second kind of moment. In other words, if we see, this time I didn't draw a three-dimensional rigid body, but you assume this is the rigid body, for example, right? Whether point A, point O, whatever points are in the rigid body or on the surface, doesn't matter. Okay? So just assume we have large enough rigid body. And first of all, there is a force acting on point A. There's a force, F, in three-dimensional setting, acting on point A. Then this time we are talking about the moment of this force about a given axis. This given axis is any axis you can pick. Okay? So this direction doesn't mean it has to be parallel, doesn't mean it has to be perpendicular, whatever. There's no requirement. Any arbitrary given axis, now it is our job to calculate the moment of this force about this given axis. Or we can even make it more general. Instead of having this given axis L passing through the original point, we can even make it more general. Say there is a force acting on this point A, so we have a large enough rigid body. and there's a force acting on point A, then what is the moment of this force about this given axis? You see, this time, this given axis is not passing through point O. So it just basically saying this can be any given axis. Of course, given axis means you need to know the direction. In other words, you need to know lambda, right? Okay. So before we officially introduce the definition of this moment of a force about a given axis, because this second kind of moment is somehow dealing with the dot product, or called the scalar product. So I'm going to just spend 1 or 2 slides, right? 2 slides to introduce the scalar product. This is different from the previous vector product we introduced before. So we're going to talk about a scalar product between 2 vectors this time. So we have a vector P, we have a vector Q, and the angle between these 2 vectors is theta. Then what is the scalar product? Sometimes we call the dot product, because this is the symbol we use to distinguish the cross product. We use a cross, right? So P vector dot Q vector, which is called the scalar product. So by definition from math, this dot product is the magnitude of the first vector times the magnitude of the second vector, and then this time times cosine of this angle between the 2 vectors, which is called theta. So this is the definition of what we call the scalar product. In addition, we don't need to worry about the direction this time. Unlike vector product, if we say P cross Q, not only we need to know the magnitude of the result, we also need to know the direction, because by definition, vector product give you a vector. That means magnitude is not enough. You also need to identify the direction. But scalar product, or called dot product, the result is a scalar. If it's a scalar, then we don't need to worry about the directions. So that's all we need to have. So we just need to calculate the scalar product, which is P times Q times cosine theta. And we don't need to worry about the directions, because by definition, the result is scalar. Okay? So this product, from this definition, you can easily see the properties of scalar product should be commutative, because P dot Q should be equal to Q dot P. And previously, with a vector product, P cross Q is not equal to Q cross P. But this scalar product satisfies the commutative rule. In addition, they are also distributive. In other words, P dot Q1 plus Q2, you just separate like a P dot Q1 plus P dot Q2. This is the same with a vector product, because if this cross, that's also okay. And this scalar product is now associative. In other words, P dot Q and then dot S is equal to what? Well, first of all, we never write like this, because if you have a P dot Q, the result is already a scalar. Then there's no scalar dot with a vector. We don't define that. So that's why it's called undefined. Okay? So just from this definition, we can easily figure out this kind of 3 properties which we are going to use, the top 2 in fact, right? However, again, we're not going to use this to calculate the scalar product, even though it's a definition. But normally, we use this way to do the scalar product, because that is more straightforward. If you use this way, then you need to know the magnitude of P, you need to know the magnitude of Q, which are okay. But how are you going to get the angle between 2 vectors? Sometimes it's a challenge. That's why, in reality, we don't use this equation to calculate the scalar product. Instead, we are going to use this way, which is always called the component method. Okay, that's why starting from chapter 2, previous one, I always emphasize everything can be solved by the component method. You just need to figure out the components. If 2-dimensional setting, you need to calculate the x component, y component of any vector, and 3-dimensional, you need to add the third component. And then you do the formulations based on the component method. Back to this one, you have a P dot Q, which is vector product between 2 vectors. What you need to do, instead of using this, you just basically split or calculate the 3 components of this vector P, and then write like this. And then dot Q, which are the 3 components with I, J, K directions. And then we're going to use these 2 properties to do the calculation step by step. In other words, because they are distributive, then you use this one times this, plus this one times this, plus this one times this, and so on. Again, in general, you should have 9 terms as well. Okay? But before you do the real calculation, you're going to see always as I dot I or I dot J or I dot K and so on, right? So now we need to know this. So these are the basic ones we need to know. Once we know these, then we can easily do the scalar product. So first of all, let's look at I dot I. What is I dot I? Okay, again, I is a unit vector in x direction, right? Unit vector in I direction. So by definition here, this time we have to use the definition because before we know this one, that's the only way we can use. The magnitude of I equal to 1 dot another I, the magnitude of the second I is equal to 1. So that means 1 times cosine theta. But these two vectors are the same. What is the angle between these two same vectors? That's 0. If 0, what's the cosine 0? No, cosine 0 equal to 1. Okay, so 1 times 1 times 1. So that's why you finally end up with 1. Okay, so now once you understand the reasons, you need to memorize this. Same thing for J cross J. Same thing for K cross K. Because, I'm sorry, not cross, dot, right? So one vector dot with another vector. If they are unit vectors, they always equal to 1. However, let's deal with another one, I dot J this time. So what is I dot J? Well, the magnitude of I equal to 1 and the magnitude of J equal to 1, that means 1 times 1, then times cosine theta. So I and J are perpendicular, right? X, Y, Z directions. So then the angle between any two orthogonal directions is 90 degrees. So what is a cosine 90 degree? Cosine 90 degrees is always 0. Right? So if always 0, even though this is 1 times 1, but finally times 0, then the result is 0. If that's the case, you can easily figure out, in reality, this is 0. Same thing for J dot K, same thing for K dot I. So any two orthogonal vectors, if you want to do the scalar product, or you want to do the dot product, the result should be 0. It's simply because the angle between these two vectors are 90 degrees, and cosine 90 equals 0. Okay, so I hope you can easily understand and memorize these. Then with this one, we come back to look at this vector P dot with this vector Q. You just do the math. This one times this. I cross I equal to 1. Well, okay, you need to have a PX, QS somewhere here. And then I cross J equals 0, then forget about this one times this. I cross K equals 0, forget about it. So then this term multiply with this one, J cross I equals 0. J cross J equal to 1, then you have a PY times QY, which is the second term. And this one times this one equals 0. And then you finally move to the third term. K cross I 0, K cross J equals 0, K cross K equals 1. Then finally you have this a PZ times QZ, which is here. So if you want to calculate the dot product between two vectors, this is what you'll finally end up with. Okay? As a special case, instead of P dot Q, what is a P dot P? Well, that's easy. That means Q equal to P. That means QX equal to PX. PX squared. QY equal to PY. That's square. QZ equal to PZ squared. So PX squared, PY squared, PZ squared. What's this one? This is the square of the norm. If you have a vector, right? In fact, if you want to calculate the norm, then you can do this as well. Okay, but it's a square because this is exactly the definition of the square of the norm. Okay, so by going through this one, we should have a better idea to deal with the scalar product between two vectors. Now let's talk about something further in terms of these kind of two list things. Number one, in reality, this slide is very helpful for you to calculate some math problems. So if you deal with geometry problems in math and you have two vectors, okay, you have two vectors, and if somebody asks you to calculate the angle between two vectors, how are you going to do that? Well, this is the equation. This is exactly the scalar product definition. First of all, when we have a P dot Q, from the definition, that is a PQ and then cosine theta from the definition. But I told you, normally we don't use this. Instead, we use the components of P and the component of Q. We end up with this one, right? But then, of course, this one should be equal to this as well from the definition. Then look at these two equations, these two terms. This one equal to this. assuming you know P, assuming you know Q, then actually from this you can calculate cosine theta. That's the angle between two vectors. So this is actually the very popular equation allowing us to calculate a pure mathematical problem by finding the angle between two vectors. Okay? But this is not what we want to emphasize in statics, because that statics is the physics, right? So, but just to let you know, since you know scalar products, sometimes you can easily calculate the angle between two vectors. The real thing I want to emphasize is the second part, which is the projection of a vector on the given axis, because that's directly related with the second kind of moment we're going to talk about. Okay? So, but this is a math definition. What is a projection of a vector on the given axis? Okay, let's take a look. For example, we have a vector P. This time you don't have to assume P is a force because we're talking about math, still talking about math now, right now. So we have a vector P. So then what is a projection? What is a projection of this vector P on this given axis, which is called OL, for example? Well, from geometry, this is the projection. If you have a parallel light, okay, shining from this direction to that axis, then this is the projection, the shade area, right? The length. So OA is the projection. Okay? So from this triangle with a right angle here, then the projection OA should be equal to the magnitude of this vector P multiplied cosine theta. So that's the definition of the projection of a vector about that given axis. So P times cosine theta, that's a projection. And normally we say POL, because this OL is that line. It's a projection of vector P along OL axis. This is the definition. Now, on the other hand, let's say we have a general vector along this OL direction. We call Q. Okay, so we call Q. So Q is another vector along this OL direction. So then what is a P dot Q? P dot Q in general, that should be equal to the magnitude of P multiply the magnitude of the Q, and then multiply with the angle between these two vectors, theta. So the right hand side gave you a scalar, so that means this Q is it's just kind of a number. So then we can put this Q to the left hand side, then the right hand side has P cosine theta left. But the left hand side, you need to put this Q. This Q is different from this Q. This is a vector Q. This is a magnitude of the Q, right? So in the denominator, which is allowed because it's a scalar. So now, what is a Q vector divided by Q? That's not equal to 1, okay? Because this is a vector divided by its own norm. Q vector divided by Q, that's exactly the unit vector, which is called lambda. Okay? So Q vector divided by Q, that's exactly lambda, which means the unit vector of this line. The unit vector of this line. So then you have a P dot lambda, because this is the unit vector of that line. P dot lambda, in fact, is finally called the projection of this vector P in this line. And of course, if you want to do the math, that's going to be the components of x components, y components, z components, multiply the 3 component lambda, that's the direction cosine, cosine theta x, cosine theta y, cosine theta z, right? So the most important thing I want to emphasize this equation. So if you want to calculate the projection of a vector about a given axis, and this is the equation you need to use to calculate such projection. Okay? Which is a dot product between that vector dot with the unit vector along this given axis.